Friends, the next question that we are going to look at is question number 26. Now in this question, a lossless transmission line having a surge impedance loading of 2280 megawatt is provided with a uniformly distributed series capacitive compensation of 30%. Then the surge impedance loading of the compensated transmission line will be is what is the question. So a lossless transmission line having a surge impedance loading SIL is equal to 2280 megawatt is provided with a uniformly distributed series capacitive compensation of 30%. Then the surge impedance loading of the compensated transmission line will be is what is the question. So what is our surge impedance loading? It is equal to 2280. Surge impedance is equal to ZC. And then what is surge impedance loading? Surge impedance loading is equal to V square divided by ZC. So this is very important equations that we are going to derive in this problem. So the intermediate equations, all these intermediate equations you have to put it in the box. So you can see that the surge impedance loading is inversely proportional to ZC. And now we are going to calculate the compensation, the series compensation that is provided into the system. And it is said that the series compensation that is provided is 30% compensation, and therefore we are going to find out the series reactance of the line. So what is the net reactance is equal to j omega L minus 1 divided by j omega CSC, and reducing this expression it will come like j omega L into 1 minus Cx CSC divided by XL. And instead of X CSC divided by XL, I am going to substitute gamma SC. So it becomes j omega L into 1 minus gamma SC. And gamma SC here is known as the degree of the series compensation. So we can write the expression relating the surge impedance loading to the compensating impedance. SIL2 divided by SIL1 is equal to ZC1 divided by ZC2. So that is the fundamental equation. So here SIL1 is given. We will have to find out the value of SIL2. Now we have found out a relation with respect to ZC1 and ZC2 with respect to the series compensation that is given. Initially there was no compensation, so the uncompensated line had a surge impedance loading of 2280. Now the line is compensated with a 30-degree compensation. So and it is going to become the gamma SC. So what is SIL? So this expression you can write it as SIL2 divided by SIL1 is equal to ZC1 divided by ZC2. So you have to put this expression in the box. And from this SIL2 is equal to SIL1 into ZC1 divided by ZC2. So what is the ratio? The ratio is root of 1 minus gamma SC. And gamma SC is given as 30% compensation, which is equal to 0.3. So what is SIL2? SIL2 comes to 2725.12 megawatt. So what will be our answer? Our answer is 2725 megawatts. So for question number 26, we will go with the option C. Moving into question number 27. For a fixed value of complex power flow, what is complex power? S is equal to P plus JQ. Okay, so that is what is complex power. In a transmission line having a significant voltage V, the real power loss is proportional to what is real power loss? Real power loss is proportional to I square R, isn't it? So what is complex power? Complex power is S is equal to V into I. Or what is I? I is equal to S divided by V. So what is the real power loss? Real power loss is I square divided by R. Instead of I, you will be able to substitute S by V the whole square. So it is S square R divided by V square. Or we see that the real power loss is inversely proportional to the square of the voltage. So real power loss is inversely proportional to the square of the voltage. So that means the real power loss will be proportional to 1 divided by V square, which is option C for question number 27. Moving into question number 28. A 50 Hz synchronous generator is initially connected to a long lossless transmission line which is open circuited at the receiving end. With the field voltage held constant, the generator is disconnected from the transmission line. Which of the following may be said about the steady state terminal voltage and field current of the generator? So we will have to check for the steady state terminal voltage of the generator and also the field current of the generator. So a 50 Hertz synchronous generator is initially connected to a long lossless transmission line which is open circuited at the receiving end. Whether the field voltage held constant, the generator is disconnected from the transmission line. Which of the following may be said about the steady state terminal voltage and field current of the generator is what is the question. Now, as the field voltage is held constant, the field current will also be constant because it is not going to change because the field circuit is closed. When the generator is connected with open circuit transmission line, the line only draws the charging current IC. Therefore, Vt is higher than that of the generated EMF Eg because the charging current is only being drawn. So the terminal voltage is greater than the generated EMF. But when the generator is disconnected from the line, there is no charging current delivered by the generator. So the charging current becomes equal to 0 and Vt becomes equal to Eg. So the terminal voltage will decrease. So we will check for the options. The magnitude of the terminal voltage decreases and the field current does not change. So our answer is option A for question number 28. Moving into question number 29. The horizontally placed conductors of a single phase line operating at 50 Hz are having outside diameter of 1.6 centimeters and spacing between the centers of the conductors as 6 meters. The permittivity epsilon of free space is given as 8.854 into 10 raised to minus 12 farad per meter. The capacitance to ground per kilometer of each line is. So we will have to find the capacitance to ground, and we know the direct expression of capacitance as C is equal to 2 pi epsilon 0 divided by Ln D divided by R. All values are given. You just substitute. So what is our answer? Our answer becomes equal to 8.4 into 10 raised to minus 9 farad per kilometer. So what is option? Our option is option B, which is 8.4 into 10 raised to minus 9 farad per kilometer. Now moving into question number 30. In a long transmission line with the R, L, G and C are the resistance, inductance, shunt conductance and capacitance per unit length respectively. The condition for distortionless transmission line. So this is the direct condition that we have obtained in the theory portion. The condition for the transmission line to be distortionless is R by G is equal to L divided by C. So you have to by heart this condition. R by G equals L divided by C, which is equal to option A, because R by G is equal to L by C, or RC is equal to LG is the answer for question number 30. Moving into question number 31. For a fully transposed transmission line, positive, negative and zero sequence impedances are equal. Positive and negative sequence impedances are equal. Zero and positive sequence impedances are equal. Negative and zero sequence impedances are equal. So what will be our option? Our option will be option B, because for a fully transposed transmission line, positive and negative sequence impedances will be equal and zero sequence impedance will be different. So 31, our answer is option B. So these are already all questions, all theory portions that we have discussed while we were discussing the theory portions. So these are already discussed because we have already, I have already given you the conditions of positive, negative and zero sequence impedance of transformers, transmission line, alternators, and also with respect to every fault condition we have derived the values of the positive, negative and the zero sequence impedances. Now moving into question number 32. For a 400 kilometer long transmission line, series impedance is given and the shunt admittance is also given. Now the magnitude of the series impedance in ohm of the equivalent pi circuit of the transmission line is what is the question. So this is a 400 kilometer long transmission line. Z per kilometer is given, admittance per kilometer is given. So it is Z per kilometer. So multiplying it with respect to the distance, it becomes equal to capital Z. A Y is given. We are multiplying Y with respect to L. So it becomes total Z. So this is the total impedance of the line and this is the total admittance of the line. And what is gamma L? Gamma L is equal to root ZY, from which we will be able to find out the value of gamma L as J 0.6324. So now you see that there is no real part for gamma L. So gamma L becomes equal to 0 plus j beta L. And what is to be found out? We will have to find the magnitude of the series impedance of the equivalent pi circuit of the transmission line. So what is the value of the series impedance? ZC is equal to root Z divided by Y. So it becomes equal to, when you are substituting this, it becomes equal to 316.22 ohms. So this is our equivalent pi network of the system. So here you can see this is Z dash and this is Y dash by 2 and Y dash by 2. And what is Z? The net Z is equal to ZC sin H gamma L. So you can substitute the value of ZC and the value of gamma sin H gamma L, because you can convert this into, because the alpha L will be equal to 0, you will have to substitute the value of the beta L. Okay, so this becomes equal to ZC into sin 0 into cos beta L plus j cos H alpha L into sin beta L. Okay, so when you are substituting all these values, you will get the value of impedance to be 187 ohm. It is obtained as 187 ohm because there is no value of alpha. Alpha is equal to 0. Only value is of j beta L. And what is j beta L? J beta L is equal to this value. And ZC is also obtained as 316.22. So you will have to substitute all these values into this expression of ZC sin H gamma H alpha L minus ZC sin H alpha L cos beta L plus j cos H alpha L sin beta L. So answer is obtained as 187 ohm. So this is a numeric question. So what is our answer? Our answer is 187 ohm. So that is the series impedance in ohm of the equivalent pi circuit of the transmission line. Moving into the next question, which is question number 33. A composite conductor consists of 3 conductors of radius r each. The conductors are arranged as shown below in symmetrical spacing. The geometric mean radius of the composite conductor is kr. If it is kr, then the value of k. So we will have to find the GMR of this system. So we are going to find out the geometric mean radius of the system. And what is the geometric mean radius of the system? Because there are 3 conductors in the system and each conductor is separated by 3r. So when we are considering one single conductor, it becomes equal to 0.7788 r. So it becomes equal to 0.7788 r into 3r with respect to the other conductor and 3r with respect to the other conductor. So the net geometric mean radius becomes equal to 0.7788 r, which is the self of the conductor under consideration, into 3r with respect to the other conductor and into 3r with respect to the other conductor, the whole cube and the whole raised to 1 by 3 square. So it becomes equal to 0.1913 r, which is equal to kr, or what is k? K is equal to 1.913. So value of k is equal to 1.913. So that is answer for question number 33, 1.913. Now moving into the next question, question number 34. A single phase transmission line has 2 conductors, each of 10 mm radius. These are fixed at a center to center distance of 1 meter in a horizontal plane. So a single phase transmission line has 2 conductors, each of 10 mm radius. Each of 10 mm radius and a center to center distance of 1 meter. So a center to center distance of 1 meter, which is equal to capital D. This is now converted to a 3-phase transmission line by introducing a third conductor on the same radius. This conductor is fixed at a equal distance d from the 2 single phase conductors. So the 3-phase line is fully transposed. Positive sequence inductance per phase of the 3-phase system is to be 5% more than that of the inductance per conductor of the single phase system. So the distance d in meters is to be found out. So the third conductor is fixed at an equal distance d from the 2 single phase conductors. Okay. So we will have to find out the difference between the first arrangement and the second arrangement. Okay. So this is the first case. The first case is that A and B are having is a single phase system, with A and B separated by 1 meter distance and each of radius is equal to 10 mm. So here we are going to calculate the value of the inductance of the conductor. So when you are going to calculate the inductance of the conductor, it becomes equal to 2 into 10 raised to minus 7 ln D divided by R. So L1 becomes equal to 0.97, and then what is L2 is the difference. So it is converted. These are fixed in a center to center distance of 1 meter in a horizontal plane. It is now converted into a 3-phase transmission line by introducing a third conductor, which is at a distance of D. Okay. So the positive sequence inductance per phase of the 3-phase system has to be 5% more than that of the inductance of the conductors of the single phase system. So we are going to increase it by 5%. So when your L1 is equal to 0.97 microhenry per meter, what is our L2? L2 is 5% greater than that of the 0.97 microhenry per meter. So it is because it is 105%. 105% is 1.05 into 0.97. So L2 becomes equal to this much Henry, which is equal to 1.0185 microhenry per meter. And when you are going to make the same equation with respect to capital D, and when you know the value of L2 you can substitute L2 with 1.0185. So substituting L2 with 1.0185 and solving this expression, this becomes equal to Ln is equal to this, and it becomes equal to this, and this can be converted to E raised to form, from which you will be able to isolate the value of D. So what is the value of D? The value of D becomes equal to 1.427. So that means the third conductor is inserted with respect to an equal distance of D with respect to other two conductors. Now what is the distance D? It is 1.427 and it is 1.427 symmetrically with respect to the other two conductors. So this is also a very good question. So what is our answer? Our answer is equal to 1.427. That is the distance D in meters. Okay. So that is about question number 34. Now moving into question number 35. At a no-load condition, a 3-phase 50 Hz lossless power transmission line have a sending end and receiving end voltages of this. Okay. Assuming the velocity of traveling wave to be the velocity of light, the length of the line is to be found out. So similar kind of a question we have already done in this chapter. So what is our equation? Our equation V of S is equal to A times VR. And from this we will be able to find out the value of A. And then what is A? A is equal to 1 plus YZ divided by 2. So Y value, Z value we don't know. We will have to find out the length of the line in kilometers. So for a lossless line, it is already given as it is a 50 Hz lossless line. So that means R is equal to 0, G is equal to 0. So R is equal to 0, G is equal to 0. Then A becomes equal to 1 minus omega C into omega L divided by 2. And then what is beta L? Beta L is equal to root omega L omega C. A value can be, A value is already found out. So we will be able to substitute the value of A, and then 0.9524 is equal to 1 minus omega square LC divided by 2. So it is omega square LC divided by 2. From this expression of A related to L, so what is A? A is also equal to 1 minus beta square L square divided by 2, and then A is equal to 0.9524. So that means 0.9524 is equal to 1 minus beta square L square divided by 2. Beta L can be obtained from this expression. So beta L becomes equal to 0.3085. So 0.3085. So what is beta? Beta is equal to 0.3085 divided by L. And there is another expression, V divided by F is equal to 2 pi divided by beta. So this expression is also made in the theory. So it is V by F is equal to 2 pi divided by beta. Beta is equal to this. So V by F can be substituted, and 2 pi divided by beta, instead of beta we will be able to substitute 0.3085 divided by L, which will give you the line length to be 294.59 kilometers. So this is also a very good question which involves about 4 to 5 equations. So these are simple equations, but if you don't know the equations, then you will not be able to do the problem. So you have to practice these kinds of questions over and over again, that the equations will come to you fluently depending upon the value to be found out. So what is L? L becomes equal to, because the only value that we know in this equation is L. So L becomes equal to 294.59. So what is the value of L? It is equal to 294.59. So it is 294.59 kilometers is the length of the line. So this is also a numeric question. Okay. So this is the answer for question number 35. So these are the previous GATE questions with respect to our chapter 1 transmission lines. So we have did some questions with respect to short line, medium line and long line. Also we have did some questions with respect to compensation, and also with respect to alpha beta parameters, also finding the length of the line with respect to the capacitance and the inductance and the impedance of the line. We have also did some questions with respect to the surge impedance and also with respect to the surge impedance loading. So all these questions are really very important, and we have did some questions with respect to the configurational arrangements of the line, and also with respect to positive sequence and zero sequence components also. So positive sequence, negative sequence and zero sequence components problems we will be doing in detail while we are going to do the chapter based on the fault analysis. So these are all the questions which are previous GATE questions with respect to our first chapter of power systems.